sponsored by Brilliant. This is a $300 GoPro, and I'm going to destroy it with a Dremel. This gets me access to the sensitive electronics inside. I'm going to remove some parts, swap a few cables, and add some mystery sludge. And through this process of deconstructing the camera, I'll end up with the perfect solution to capture good, high-quality onboard video from the rockets I fly. I used to be a professional videographer, so I think about bitrate and resolution and frame rate and color science quite a lot. GoPros are far from the only option for getting high-quality video from a rocket. But over the years that I've been doing this, they produce the result that I like the best. If you want recommendations for cameras that don't cost as much and are a little less complex, stick around to the end of the video. But for now, we're going pro. We're going GoPro. This is the Hero 10 Bones. GoPro came out with it a few years ago, and it's marketed toward FPV quad enthusiasts. The Bones is an interesting product because there's no screen or battery, just 2 buttons, an SD card slot, and a lens. The footage that comes out of this thing is just as good as any other GoPro, and it's capable of the frame rate resolution combo that I love, 4K, 120 frames per second. I've launched rockets with this camera on board several times, but there are 2 major problems with it. It overheats. This is basically an oven that happens to shoot video, and the form factor is not good for rockets. In most of the rockets I fly, I'm kind of obsessed with getting that down-looking shot. This means the camera needs to poke outside of the airframe just a little bit so that we can see the ground as it falls away. There are several cameras that are great for this out of the box. This right here is the RunCam Split 4. The sensor package is separate from the recording and FPV package. This makes it easy to just stick the sensor and lens outside of the airframe, which minimizes drag, while still giving a pretty good result video-wise. The down-looking shot is always going to be more dynamic than a shot that looks out at the horizon, especially if you don't have roll control. I don't know about you, but I like the shot on the left more than the shot on the right, and I'm happy to pay for that shot with a slightly lower apogee. Even at the small scale, when I landed this model rocket, the imagery from the booster looking down is a lot more compelling than it would have been had it been looking at the horizon. Of course, you can always take this to the extreme. This is some footage from when I mounted a 360 camera on the top of a rocket, but I find this a little bit jarring. This GoPro is a huge brick, and you don't really want to stick this whole thing out the side of an airframe. I did a version of this about 2 years ago where I tilted the camera outside the rocket and covered it in hot glue. The results were pretty good, but it's still very draggy. I know we can do better, and I'm mostly saying that because I've already done it and now I'm making the video about it. I start by running a cutoff wheel around all sides of the camera. The shell of the camera seems to be joined by epoxy or some other permanent molding technique. There are no fasteners on this to remove the parts. But once the camera's open, we get access to a similar setup with the RunCam. The sensor package is attached to the rest of the recording hardware via a small ribbon cable, and if we're really careful about it, we can rotate the camera lens in a bunch of different directions. This is all well and good until we remember that this camera overheats when you look at it the wrong way. Here's a runtime test to show you what I mean. Running at 4K and 120 frames per second, I ran the camera until it overheated. The camera shut off a little shy of 5 minutes into recording. I have found a way to solve this issue. It's dumber than you think, but stay tuned and I'll tell you in a minute. Cutting the camera open is a nerve-wracking process because you're using a cutting wheel right next to the sensitive electronics, and there are other options. The first camera I tried this on is made by a company called Flywoo. Made is maybe not the right word. Modified and then resold is better. Flywoo makes what they call a naked GoPro. They buy a GoPro 10, take it apart themselves, then add several extra features. These include things that the GoPro Hero Bones doesn't have, like a screen, a fan, and a buzzer. You do pay extra for this, but as an advantage, the camera can be taken apart with a screwdriver rather than a Dremel. Either way, whether it's the Flywoo product or the GoPro Hero Bones, you're left with the same package, a sensor element and a control board. On the Hero 10 Bones, in order to remove the case, I had to make some pretty nasty cuts into this metal. The aluminum frame is important for heat dissipation, and if you were flying FPV, like is intended for this product, the airflow over this front plate would help cool the camera down a lot, and you'd likely see much more than 5 minutes of recording. The airflow of a rocket is pretty good too. The problem is that most of the time the camera is either burning on the pad or burning above the atmosphere, so the cooling of flight does not really help here. The sensor element is held on at 3 points, and I trim all those points off because we're not going to need them anymore. And most of the screws here are T5 bits, although some of them are Phillips head, which, GoPro, you guys all right over there? Inappropriate Phillips head hardware is kind of my thing. Next, we need to remove this plastic backing plate. This helps keep the sensor ribbon cable attached, and it pushes against the back plate of the camera. In what I imagine was a last-ditch effort in terms of thermal reliability, GoPro have opted to put a piece of thermal tape that attaches to the back plate of this plastic. I can't imagine this does much, so I've just been cutting it off and I see no difference in performance. So the sensor ribbon cable is a little shorter than I would like. You can get the sensor to do about a 90-degree turn before the ribbon cable seems very stressed, but especially in a high vibration environment, this does not pass a vibe check, so I'd like to replace it. In order to remove the ribbon cable, we need to remove the backing plate from the sensor itself. And as part of this process, I'll also remove some of this thermal tape from what seems to be a heatsink pad. Next, I'll remove this Kapton tape over the lever connector, and then carefully lift the connector up to remove the ribbon cable itself. I found this replacement cable on AliExpress. That's a dangerous sentence. It's a little bit longer than the stock ribbon cable that GoPro provides, and it was pretty cheap, so I ordered a few of them. Swapping in the new cable is easy. It goes in exactly as it comes out, and now we have a much greater range of motion with the sensor element. At this point, it's probably worth turning the camera on to make sure it still works. I'm viewing the current draw from a power supply. Since we don't have a screen or buzzer and just one LED on the camera, we have to rely on the current sense from the power supply to see what's going on. At 9 volts with a setting of 4K 120 frames per second, we should be pulling about 700 or 800 milliamps. The camera seems stuck at 300, and the LED won't blink at all. To make sure I wasn't missing anything, I replaced the AliExpress cable with the original GoPro unit. This worked without issue, and you can see about 500 milliamps on the power supply. This is because we're recording at a lower frame rate, so the camera is drawing less power. I'll spare you the details, but after looking at it under a microscope and swapping out the cable 3 different times with the different units I ordered, I could not get this thing to work. After doing a little more digging, I found another replacement cable from a company called Red Kite Drones. They sold the cable in several different lengths, which is big thumbs up for me, who wants to put cameras in weird places, and the cable is a good bit more expensive than the AliExpress unit. But big smooth brain up here, more expensive must mean more better, right? I opted for the 90-degree turn ribbon cable because it seemed interesting, and swapping it out was as simple as before. The range of motion achieved with this is better than the AliExpress unit as well, and I imagine the longer cables are even better. This means we can make those 90-degree turns or twists without stressing the cable too much. As I pop the SD card back in the camera to test it, we should talk about another mod that I like making on these cameras. I am particularly fond of these little micro SD extension cables. You can get them in various lengths, and especially for situations where the cameras are deep inside of a tube, if you can't access the camera, you can probably run the ribbon cable to a point where you can access the SD card. I've done a bunch of testing with these and have yet to find a cable that doesn't support really high bitrate GoPro video, but there is certainly a limit on how long these cables can run. You cannot daisy chain them together. That does not work. Anyway, the 90-degree turn Red Kite Drones cable worked just fine, so we now have a GoPro Hero 10 deconstructed in a much better form factor. It's pulling between 700 and 800 milliamps, the LED is blinking, the files are recording. But I should back up here. How do we get this camera to record 4K 120? It doesn't ship with those factory settings. This is my favorite part about GoPros, and just as a note, this video is not sponsored by GoPro. They have no say in this. If you work at GoPro, please reach out. I would like to be sponsored by you guys. I just can't get in touch. Anyway, this is my favorite part about them. It's called GoPro Labs. Every one of these little cameras ships with firmware that can read a QR code. That QR code lets you control every single conceivable setting on the camera, and oftentimes much more than you'd find in the stock menus with a GoPro that has a screen. Using an app on your phone, you can generate a QR code that has all the specific settings you want on your camera. And if you're wondering why this QR code keeps changing, it's because you're setting the time to a sub-second accuracy. That means even if you take this thing apart, put it in a rocket, it's mounted there forever, and you realize last second that you want to change the settings, all you've got to do is take your phone out, generate a QR code, flash it to the GoPro, and that's it. No buttons, no screens, no Bluetooth, just vibes. Drawing 750 milliamps is ideal, but of course we aren't going to draw that for long. This thing doesn't record for more than 5 minutes. Let's fix that. I'll start by taking the control board off of the aluminum backing plate. Once again, we're using mostly T5 screws and 2 strange Phillips head screws. I don't really understand this. The board folds open around a ribbon cable, and I'll start by removing some of this thermal paste. This helps transfer the heat out of these processors and into the aluminum backing plate. The plate has this black coating, which I expertly managed to scratch, and the black coating is a dielectric, so I used a bit of Kapton tape to make sure that we couldn't short out against the plate here. By default, this plate also has the microphone connected to it. You've got to be careful about this ribbon cable because you don't want to break the microphone. And if you flip the backing plate over, you can see this small hole, which is the mic hole. If you manage to cover that in epoxy, your flight is going to sound like this. This is not the most compelling sound I've ever heard from a rocket, but let's head back to the sensor board and deal with this heat issue. I'm going to cover this whole space in XTM50 thermal paste. The brand or model of thermal paste doesn't matter too much here. We're covering so much surface area that I can't imagine any thermal paste will do that much better or worse. The only important thing with this thermal paste is making sure it's a dielectric, otherwise you're shorting out all of your electronics. I use a little plastic spudger to make sure the thermal paste gets all in these little components. In all likelihood, and given the cost of thermal paste, this is pretty overkill. The two processors that we scraped the thermal pads off of are probably the only things producing significant amounts of heat. My bet is that you could accomplish the same result with like half the thermal paste. Our goal here is to increase the contact area to this backing plate, and once that's done, I'll replace the screws. Next, we're going to repeat this thermal pasting process at a slightly larger scale, and our goal here is going to be to increase the total thermal mass of the camera. Stop playing with it. Stop playing with it. You're going to break the ribbon cable. Put it down. Thank you. Using the same XTM50 thermal paste, I'm going to coat most of this backing plate. I'm only coating the section where most of the heat is generated, and specifically, I'm not coating the section where the mic hole is. My goal here is to increase the thermal mass of the camera, kind of literally, and we're going to do that with just over 30 grams of aluminum. This 1/4-inch aluminum block is going to get thermal pasted to the aluminum backing plate, and with it attached, I'm going to use some IPA and a paper towel to make sure none of the thermal paste is squeezing where it shouldn't. We aren't actually solving the heat issue. We're putting a band-aid on it. I don't care if this camera overheats, I just want it to overheat way later than it does. By increasing the amount of material that is thermally tied to the processors need to heat up all of that extra aluminum before they can actually overheat. And using lots of thermal paste makes sure that all of that heating rises at about the same rate. I've run this experiment several times now. What you're seeing on screen is about 45 grams of aluminum. And how long would you guess the camera runs for at 4K 120 FPS? It's certainly longer than 5 minutes, longer than 10, longer than 15. It's longer than 20. It's longer than 30. It's not 35. It's not 40. The camera dies just after 45 minutes of runtime, significantly better than the sub 5-minute number we were getting out of the box. I ran a bunch of these tests 2 weeks ago on a live stream on this channel. If you don't believe me, I don't know why you wouldn't, but you can go in the description and watch it happen in real time. And using a thermal camera, we can see how hot things get. On average, I've seen the camera get up to about 180 or almost 200 degrees Fahrenheit, and as the temperature keeps rising and it warms up that aluminum block, eventually it overheats. 45 minutes of recording time is far more than I need for most flights, so we can take advantage of this in a couple of ways. Reducing the mass of the aluminum is one way, but another is to just toss a second camera on the same piece of aluminum. Last spring, I ran a series of roll control test flights, and I wanted some high-quality footage from GoPros on there, but the cameras were flying in a 2-inch diameter airframe, which is not a whole lot of space for a camera this size, even if you deconstruct it. I took the same approach as shown earlier, covering as many parts in thermal paste as I could, and in this shot, you can see me accidentally cover the microphone in thermal paste, which is how I got that clip from earlier. I used about 50 grams of this 1/4-inch aluminum and thermal pasted a camera to either side. With both cameras running, the time to overheat was just under 13 minutes. This is a fairly short period of time. I use a telemetry signal and AVA to power on the GoPros, so I'm able to arm the GoPro 30 seconds before launch. But even still, 12 minutes of time is not great, but that time is about to go up. The form factor of these cameras is kind of messy, and especially in a 2-inch build, there's not a lot of room for designing a very elegant part that doesn't take a lot of work to manufacture. So I mounted them inside the rocket using a bunch of epoxy filled with Kevlar pulp. This is some of the grossest stuff I've ever worked with, and it yielded equally gross results on the outside of the rocket. Sometimes when people make a mistake in painting, they call it a 5-foot paint job or a 10-foot paint job, which means it looks okay when you stand from about that far. This is about a 400-foot epoxy job. Even though the epoxy isn't the best thermal conductor, it does still add to the thermal mass of the cameras themselves. This resulted in a thermal shutdown time of up to 18 minutes, which is much more room to breathe. Back to our single camera here, after thermal pasting the aluminum to the body, we have to make sure to clean up all the thermal paste around the sides. I'm going to use 5-minute epoxy to lock the aluminum in place, as well as pot some of the electronics on the control board. And I found this out the hard way. The thermal paste and the epoxy mix together like oil and water. I mean, it might literally be like that. I think there's some type of oil that makes thermal paste the way that it is. If you know what that is, just leave it in the description. Anyway, it prevents the epoxy from curing really well, so you gotta wipe off the excess. 5-minute epoxy is not the most elegant way to deal with this problem, but it does solve some interesting things. For instance, I have no interest in using the buttons on this camera again, especially given that I can do all of the programming I need with a QR code if I ever need to update. And since this is a high vibration environment, anything I don't want to move gets coated in epoxy. Other objects that benefit from this are the SD card extension, which is kind of fragile and on a little overhang diving board situation. Potting this in epoxy, or at least parts of it, help relieve some of the strain that could be felt if that cord gets yanked around. Finally, it's helpful to use the epoxy to lock the ribbon cables in place. A couple of times in the early stages of doing this modification to the camera, I had the ribbon cable snap off, sometimes in a way that ruined the whole camera. So you want those ribbon cables staying on the board. I also use the 5-minute epoxy to pot the back of the sensor package. This helps keep the ribbon cable attached, and it also increases the thermal mass just a little bit. As I mentioned earlier, I never ran into problems with removing the thermal tape that was on the sensor package, but it's possible that this could introduce issues with longer recording times. The cameras you're looking at here are going into the meat rocket, or the rocket that's going to go to Mach 3 and use the nose tip to cook a piece of meat. For obvious reasons, I want good coverage on that flight, so let's get these cameras mounted. These are going to go in a coupler section, or something that I referred to as a switch band. The switch band is going to house 2 hex screw connectors which allow us to turn the rocket on the pad, but I'm also going to make several cutouts for the sensors of the cameras. Before mounting the cameras, I attached several PWM extension cables and then used heat shrink to insulate them. Yes, you heard that right. I do know what heat shrink is, and I do know how to use it. It's just that sometimes I forgore. I'm putting 3 cameras in this rocket. One looking down, one looking up, and one looking out. Each camera has a slightly different sensor setup, which is why this longer ribbon cable is very helpful, and each camera gets mounted delicately using a little bit of 5-minute epoxy and some CA. This process is best done slowly and cautiously, and it's really easy for the epoxy to get places you don't want it, so I often cover the lens with a piece of tape while I'm setting it up. Especially with 5-minute epoxy, this works in my favor. The epoxy gets gummy before it gets hard, which means it peels off pretty easily. The double thermal paste aluminum block epoxy situation is what works best for me, but if you have more time or are interested in putting more effort into this, you could also do like my friend Sam Austin has been doing. Sam reverse engineered the bolt pattern on the aluminum backing plate and used that to create and machine his own GoPro mounts. This allowed him to thermal paste his cameras to a much nicer looking block of aluminum and with a larger thermal mass. And as with many things in engineering, I think there's just lots of different ways to solve this problem. The cameras for the meat rocket ended up getting potted in lots of epoxy, just like the 2-inch version. And if you look at this solution and think to yourself, that's $900 of cameras that are stuck in there forever, you're correct. I'm not going to do a whole cost breakdown here, but the other non-recoupable costs are the $600 tube, the $800 stock material for the fins, the servos that are $80 each. This rocket has over $1,000 in avionics, over $1,000 in some of the specific sensors on board, and all told with logistics factored in, it's like multiple thousands of dollars for this one flight. This isn't me asking for money, but I'm providing some context. $900 is not necessarily a drop in the bucket, but I too look at this and think, wow, this is kind of wasteful. It's just that the whole project is also kind of wasteful. And truly, if you want to follow this logic to its logical end, the least wasteful thing I could do is never fly any rockets. And I'm unwilling to consider that as an option. The GoPro produces some of the nicest footage that I've seen from a rocket in flight. If you're watching this in broad daylight on a phone, the difference is not going to be noticeable to you. But as a person who wants to take pride in his own projects, I really want the best footage that I can get, and the GoPro does get me that. Especially on projects like the upcoming space shot, I want footage that will stand the test of time, so maximum frame rate, maximum resolution is the way to go. One part I haven't covered yet is the electronics side, so let's do that. After providing power to the camera, it sits at a few hundred milliamps for a few seconds to boot up, and then it shuts off. To start recording, you have to pull this yellow wire to ground, and that effectively hits the shutter button. This is a pretty easy thing to set up with a telemetry system, but how do you know if the camera is actually recording? If you're not able to see the LED on the launch pad, or if you're far enough away from the rocket that it's not practical to look at it, there are several ways you could solve this issue. My initial thought was to use a photodiode epoxied to the red LED on the board, but this only tells us if the camera is recording, not what settings it's recording with, and so I actually think there's a better way. By using a current sensing circuit like this, we can toss the camera on one end and then sense the voltage at this line. This will let us measure how much current the camera is drawing, and if we read that value out over a telemetry link, we can effectively confirm that not only have we hit the shutter button and the camera started recording, but it's doing so at the correct settings. I'm going to power cameras on. Okay, power on. Voltage is dropping a little bit, 146. So Charlie, go ahead and put your face, give a little wave under the onboard camera that looks down. This approach is a lot of work. Not the current sensing thing, that's pretty easy, but taking apart a GoPro, swapping the ribbon cable, doing the thermal paste, epoxying it in various places. It makes sense for me to spend a lot of time on this because my job is making YouTube videos, so it matters that this stuff looks really good. But as I said earlier, I've been at this for a long time, and I've tried to solve the problem in a bunch of ways, so let me show you some of the other ways I've done it. At the very start of BPS, I used these little keychain cameras on my rockets. Do not use these. Do not do it. It's 2024. You can get good quality cameras for like no money. I don't know why people are still using these things. The selling point is that they're small, lightweight, and cheap. So if those things are the metrics you're optimizing for, go for it. But the quality is not that good, especially if you have a flight that's less than nominal. The next option I pivoted to was RunCam 2s, these little orange bricks on the side of the rocket. These are relatively large, but they're all self-contained and they're a reasonable price. These RunCams are an enormous upgrade from the keychain camera, and they stand the test of time. This is 8 years old now, and it still works. They're self-contained, they have a battery, and the footage quality is pretty good. 1080p at 120 frames per second, or 2.7K at 60. There are newer models of this camera, so those numbers might be out of date. I'm not going to look it up. It's no effort November. These cameras produced a lot of the nice imagery that I got from the early BPS test flights, and especially for the thrust vector control stuff I was doing, I wasn't capturing great data on each flight, and having onboard footage helped me diagnose a lot of problems. I've seen these cameras survive some pretty hard impacts with the ground, which is a good selling point, and the slow motion you get with 120 frames per second can result in some really cool imagery. I used these cameras for many years, and until I got into some really advanced rocketry, I had no reason to really upgrade. If you're looking to upgrade, the next two cameras I'd recommend are the RunCam Hybrid and the RunCam Split 4. These are pretty similar cameras, but they're different in a few key ways. The Hybrid is good for FPV footage. It has two lenses on it. One of them does analog video direct to an FPV goggle set, and the other one records to the DVR or to the video recorder board. The big deal with the Hybrid is not just the real-time video, but it can also do 1080p 120 frames per second, and you all know how I feel about 120 frames per second. In contrast, the Split 4 only goes up to 2.7K 60 frames per second. This is still pretty good, and it has a much smaller form factor on the sensor element. This is the camera that I used all over Sendit and Lumineer, and that small form factor allows you to take a relatively low hit in terms of the drag that you're adding to the side of the vehicle. From a high level, it's very easy to see the difference between the keychain camera and the RunCam 2. It's pretty easy to see the difference between the RunCam 2 and the RunCam Split. But when you go from these RunCams to the GoPro, the difference becomes less apparent, at least on YouTube. As someone who's been in professional video production for well over a decade now, I can see the difference between these two cameras clear as day, but I don't expect that that's going to be valuable to everyone, and I don't expect most people to pick up on it. That's fine. This channel is not a DIY do-it-yourself type thing. I'm trying to document my journey from knowing nothing to becoming like a real person who does aerospace things, and part of that journey is documenting it as well as I possibly can, and in a way that makes me proud of it. I feel comfortable saying that these really are the best cameras you can use for this type of thing if you're willing to put in the effort to deconstruct them and deal with all of their weird quirks. A small caveat here is the DJI Air unit. DJI came out with this really cool camera that's a similar form factor to the RunCam Split. It's a separate sensor and control board. Not only that, it also comes with a wireless transmitter, and it does digital video over air, which is impressive. The problem is that have to use these with the FPV goggles. That's a crazy choice. I cannot believe they made the camera this way. It's cheaper than the GoPro. It does very similar video specs. I have heard that it has issues with overheating, but like so does this. And maybe I'm wrong. I am often wrong. But from everyone I've talked to who has used that camera, they say you pretty much have to have the goggles to set it up. I don't want to have to buy FPV goggles to do that. Let me configure it with an app. Anyway, I'll get off my soapbox. Whatever. It's No Effort November, and it's no comprehension about why DJI did that in November. Anyway, the next step in No Effort November is for me to show you how I made a nose cone for the meat rocket. It's a really cool process. I think it's going to be a great video, and I need you to promise me that you will be on your best behavior when you watch it. I'm not going to explain why. You'll find out. Just, you need to promise you'll be on your best behavior. That's it. Now it's time for a word from our sponsor. Sorry. This video is sponsored by Brilliant. If you aren't already aware, Brilliant is an educational platform designed around the idea of learning by doing. Brilliant has been a really long time sponsor of this channel. You've probably heard me talk about them many times at this point, and it's because I love what they do. I believe in them as a company, and I think it's great to advertise learning services. Truly, one of the best ways to break new ground in your own learning journey is by putting the new concepts you learn into practice. When you work through the problems you're trying to solve in real time, you get a much deeper understanding. It's the same reason that me doing projects teaches me rocketry faster than learning through a textbook. Brilliant focuses on courses in math, science, engineering, data science, and a few other fields. And you get to play around with the fundamentals in these areas because every lesson is interactive. The end of the year is coming up, which means it's time for New Year's resolutions. I know that's scary, but if there's something that you've wanted to learn, something that's on the back burner for you, now is a great time to give it a shot. And you can do that using Brilliant. This is also a really low effort commitment to make. You can use Brilliant for 15 minutes a day. Many of the courses are structured so that you don't have to spend a ton of time out of your normal schedule to advance yourself. You can get started for free for the first 30 days by going to brilliant.org/BPS.space, which is linked in the description, or you can use the QR code that's on screen. This is also going to get you 20% off an annual premium subscription, which is a great deal. Thanks a ton to Brilliant for sponsoring today's video. Thanks to you for watching. My name is Joe Barnard. May your skies be blue and your winds be low. Goodbye.